about I start that? And Zoomers, I need to share my screen so that you can watch the quiz questions as we go through these. So that's the first thing we have to do today is talk about formative assessment number 5. Only one more. We're at that point where we can start counting stuff down. So only one more formative assessment, which is not until after Thanksgiving. The next thing you have to be working on is homework 4, which is due Monday. So that's the big one, individual writing of some kind, whether you're correcting AI or doing individual data analyses. My hope is to have those all back to you within, since we have Thanksgiving and I'll be traveling, probably 2 weeks. That way you'll have 2 to 3 weeks afterwards to make revisions if you so choose. It'll be due at the end of finals week. So I want to not rush through them so that I can read them carefully and provide you with useful feedback. Because there's nothing worse than working really hard on something and then not getting any sort of indication as to how you did. So let's not do that. So, all right then. So speaking of feedback, question number 1 is taken from a real life problem, although this was not a manuscript review, this was a job talk. So at one of the previous universities at which I taught multi-level modeling, you can choose from 3 of those, I was sick when a candidate for a job gave a presentation, and my students in the class were at the presentation, and the next day in class I was feeling well enough to teach again. They're like, listen, she said this. I'm like, is that right? I'm like, what'd she say? No, you must have misheard. That can't be what they said. But I had the job talk on tape. Yes, actual tape. This is an old story. And I watched it back, and the candidate, sure enough, said something along these lines. So preliminary analyses use multi-level modeling to handle the dependency of students nested in schools. By the way, that's a dead giveaway. Handle is a word that you use when you don't really know what you're talking about. However, because we did not find any school-level predictors to be significant, this indicated that single-level regression modeling would be sufficient. So let's take this apart. First up, do you agree with that statement or do you disagree? We'll start there. Yeah, that sounds sus to me, to use the lingo of the kids.
Oh, garbage.
It sounds like garbage. Okay, that's nice throwback. Yes, happy Garbage Day. I'm wearing my merch today. So we're collecting the garbage analyses out the door. This person did get hired, by the way, so there is a happy ending to the story, but they did not let them teach the multi-level modeling class.
That's probably
Fair, right? When I watched the video, this person was giving a very competent presentation, and when they got to this part, seemed noticeably nervous and said it really fast to like get it out of the way. And I took that to indicate that they received some bad advice that they weren't really sure about and didn't want to draw attention to it. But they did get a job, so. But this answer is garbage. So what are the problems here? Just because you didn't find something to be significant, does that mean that we don't have to address dependency?
no.
No. So what's the problem? What are the problems?
Well, all the world's a multi-level model.
Yes, it is.
So-
Everything is a multi-level model, pretty much.
So you can't just assume you get to use single-level regression.
But if you do, what are the problems that you're doing? Like what concretely? Chris, what do you think?
It seems that they're making an assumption that instead of looking at the ICC, that they're looking at the significance of a level 2 predictor in order to determine if nesting is of interest.
So they're asking a different question. So whether or not there is school dependency is a logically separate question and a prerequisite to predicting that school dependency. So just because you don't have any information about why schools would have mean differences in their child outcome doesn't mean that they don't. So that's one issue. Comment from the Zoomers, person-level factors are also cluster factors. Yeah. So what have we been talking about for like 6 weeks in a row, something like that? Level 1 predictors, people characteristics, are usually cluster things as well. So to the extent that you're fitting a single level regression model, you put in a person predictor, what cardinal sin have you committed? Yes, smushing. So you are assuming that the within school and between school effects of that predictor would be the same, or said differently. What's another way to say that?
What?
If I have a person level predictor in the model all by itself with nothing about the school that corresponds to that predictor, that's a smushing problem, right? Formally, what you're saying is that the within school slope at level 1 is equivalent to the between school slope at level 2. Said differently,
No contextual effect.
yeah, no contextual effect. That's another way to say it, which is probably more understandable in this context. You're assuming that whatever cluster variance in this predictor does not have an incremental contribution to the child's outcome. So another comment, you are assuming all the variance is level 1. Yeah, I think you could say that. You're assuming that basically all we need to worry about is the within effect. And that is probably not the case, at least in most observed variables. What if it were, though? Let's say hypothetically you go through the steps, you don't find a contextual effect, so smushing is technically permittable. If I don't have any random effects in my model, though, what kind of problem does that create in terms of believing the effect of the student predictor? Fixed slope is going to be okay if smushing is allowed, if there is no contextual effect. What about the inference about it? Standard errors, p-values, stuff like that. Radio silence. They'll be off. That is true. Yeah, wrong. Wrong. Yeah, that's the whole issue with dependency is that your model thinks you have more unique pieces of information in terms of the students than what you have. So they're not contributing as much. We talked about design effects towards the beginning of the course. That is essentially how much larger your standard errors would be if you accounted for the clustering than if you didn't. So standard errors, if you ignore dependency, are going to be too small, which means that your p-values are too small, which means your type 1 error rate is too big. So even if smushing is not a problem per se and there's no contextual effects that are detectable in the data set, the inferences you would make about the effects of your person predictors are going to be incorrect. So we don't want that either. What if, let's see, so if you were going to ask this person to formally test whether or not they needed to handle their dependency, what might you suggest they do?
Are you asking about how you change the sentence structure, or if they should do like one of those log likelihood or IPC things?
That one.
Okay. Then that's my answer.
Okay, so final answer, one of those log likelihood ICC things. Okay, so let's put that into
Okay,
sentences.
stats people, help me out.
Yep.
Say,
She's not in this class. She doesn't have to respond. She's
You
just
mean
here
for the
on
level 1
free will.
predictors?
For the outcome.
so it's the -2.
That magic number thing.
Magic number thing, -2 log likelihood. That's our index of model goodness, we'll say, fit, some would say. Log likelihood is in a scale of bigger is better. It's how tall your parameters made the data. So if we have a model that is a single level model, that assumes there's no correlation of students from the same cluster. How do we add in an expected correlation of students from the same cluster?
Adding a random intercept.
Yeah, a random intercept variance. That induces an intraclass correlation, which is the effect size that goes with that significance test. So we can do a likelihood ratio test, difference in -2 log likelihood for an empty multi-level model that has a random intercept versus a single level model that does not. That's a significance test you can do for the effect of the dependency. Intraclass correlation then is an effect size. What number does that have to be in terms of an ICC for there to be no dependency?
Greater
Yeah.
than 1. Oh,
0 for an intraclass correlation. So if my intraclass correlation is non-significant, do I still need to worry about this? I would say you do. Some people would say no. But what's going to happen to the intraclass correlation after you add in student level predictors?
will increase.
It's going to go back up. Anytime you explain level 1 residual variance, the random intercept goes up. That means the interclass correlation goes up. That means the dependency goes up. So you might start with dependency that's close to 0, but it doesn't necessarily mean it's going to stay that way. Question?
Yeah, the 20, I don't know if we haven't gotten to it yet, but
Yep.
the 20 schools part of this, how is that going to be?
Ah, great question. Have not gotten to it yet. And you had some great reviewer energy in your response today. I like that. So we haven't touched about that yet. Sampled from approximately 20 schools. So could that potentially be a reason why none of the school level predictors were significant? Yeah. Do you have a lot of power with 20 of anything? No. You need to have an effect size of approximately positive infinity for that to be adequately powered at 20. So it could be the case that we have a lot of dependency and the predictors are not informative. It could be the case that we have a lot of dependency, the predictors are somewhat informative, but we don't have the power to detect that. There's a lot of possibilities here. But the point of the story is just because you can't predict the reasons for the dependency does not mean it's not there. That'd be like a doctor saying, well, we thought you had cancer and we tried radiation and that didn't work, so I guess you don't have cancer. Yay for you. It's the same type of idea. So that being said, if you don't want to do multi-level modeling, can you think of at least 2 other things you could do? I can think of 3 actually, that would at least somewhat address dependency.
Robust cluster standard errors.
Yeah, cluster corrected standard errors. You can do that.
Fixed models.
Yeah, readily in Stata and M+. There's probably R packages for it. I'm certain someone has done it. What was the other one?
Fixed effects models.
Fixed effects models. Now, Erica, you wrote about that, didn't you? Tell us about fixed effects models.
You add the group in as a predictor, like you demicode them to account for that dependency.
Yep, so if I put in school ID as a factor variable, as a categorical predictor, I'm essentially introducing 19 dummy codes that distinguishes the means of each of the schools, thereby controlling for school dependency with respect to the intercept. However, I have not controlled for school dependency with respect to potential predictor slopes, though. That could still be in there. Like if you need a random slope, in which case, then you need 19 interactions with school ID and the predictor. And then you've controlled for dependency. So that's fine in situations in which you really don't give a crap about it, you just want it to go away, and you don't have that many. That's a reasonable solution. Cluster-controlled standard errors at least will fix the fixed effects, but the fixed effects approach is going to solve the smushing problem at the same time as well. Keep the variables as controls, the clustering variable, yep, that's it. There's one more thing I can think of, which is a hack. Not ideal, but I've made some of you do it before when I didn't want you to do a multi-level model version of whatever we're doing.
I think that we could also use some kind of demeaning approach.
That,
So we can take like the cluster mean version of those predictors and use them, assuming that level 2 or level 3 things are not included in our model.
so another alternative, if you need to do something complicated and you either don't have the sample size at level 2 to make it a level, or you, like it's a giant structural equation model or something else that's already having a lot of complexity to it, you can cluster mean center your variables, including the outcome, which we'd never do unless it's to throw it in a correlation matrix. But if you think about it, if you remove all the cluster mean differences from your outcome, that's the same thing as putting in a fixed effect for cluster ID or putting in a random effect to isolate that variance. You're removing it. So that's yet another way that you can solve the problem of dependency that you're not interested in.
So you would cluster mean center the level 1 variables.
Yep, all of them. All of them. Now that's going to get weird for binary things or categorical things. I have no idea how to interpret a slope at that point, I think, in some cases. But not wrong, just weird. So yeah, those are all things to worry about. So these models are designed to tackle 2 issues, putting this all together. If you have person slopes in the model and there's cluster level dependency, your inference about those slopes is going to be off to some extent. The standard errors are not going to be right. The slope itself is smushed, which is an empirical question whether you need a contextual effect to go with it. So cluster corrected standard errors will fix the inference, but you don't want to have a correct inference for the wrong slope. You still need to do either cluster mean centering or fixed effects or something to address the problem of separate within and between slopes for any level 1 predictor. Okay, how we doing? Want to hit pause on me for a second?
I do that at home all the time.
Yeah, that's fair.
I was like, I think class takes 3 times longer.
It may. And now you know why I never put my video on, because I don't want to be like this. You know, for,
But
while
I
you're-
want to send you so many screenshots.
Yeah, I don't mind my voice being on the internet, but I definitely don't want my video if I can help it. All right, any other comments or questions about this question? Okay. So next question then. If you're reading a research paper and someone does their fancy multi-level model, how do you know that it's been done correctly? So two-part question here. What are the indicators that the effect of a level 1 predictor has been specified incorrectly? What would you look for? Zoomers, I'm watching the chat, or you can talk to us. Your call.
I will look at the parameterization of the level 1 predictors, and I would try to see if they mention the results of some analysis for those predictors at level 1, and I will look at the notation to see what variables they are using and how the variables are being interpreted in the results section.
So their words should describe some approach to either cluster mean centering or contextual effects
Exactly,
or
yeah.
something, yes. We have level 2 variance decreases. That's one. So if you put in a level 1 predictor and it reduces level 2 random intercept variance, that can't happen. That's a Trojan horse situation where it's the level 2 variance in the level 1 predictor that did the work, which means there's a potential for a differential contextual effect that's needed to explain the rest of the random intercept. More comments. Level 1 predictor is included by itself only. Yep. If you look at a table of results and you see variables at level 1 that don't have some analog at level 2, that's probably an issue unless they've been explicitly cluster mean centered. If you cluster mean center a level 1 predictor, I'd say it's not wrong to admit the cluster mean, but it is weird. Because you're saying that the effect of having, more money than the rest of the kids or more ability than the rest of the kids, but it doesn't matter what the reference point is. That's weird to me. Not wrong, but weird. Model equation, yep. So if they don't have a table, if they have an equation, then you don't see something at level 2 that's an analog. Does it have to be the cluster mean necessarily that goes in? No? Can you think of an example in which that would be a bad idea?
You mean at level 1?
If for a level 1 predictor, if you want to not smush, if you want to specify a level 1 predictor correctly, does it have to be the cluster mean of it that goes in at level 2? What do you think? Shaking your head?
Well, if you have a binary variable, or like you always said, it makes it kind of weird and funky. So it could just be any constant center.
At level 1, that's true, yes. So the question was, do you have to put in the cluster mean of a level 1 predictor, or are there other choices potentially?
Like retirement age, you might want to choose 65 if you're on the center. That is what
Also true, but that's not what I'm asking. Let me try again, because two people just answered the same different question. So let me ask that question then. For level 1 predictors, do we have to cluster mean center them? That's the question you both are answering, I think.
Not necessarily.
Yeah, not necessarily, like if it's binary and 0 already means something, or if you have a variable in which there is a meaningful reference point, like retirement age being 65, or maybe, the transition into adulthood being at 18, legally for most purposes, something like that. As long as you put in your contextual effects, in those cases, if you don't want to cluster mean center your level 1 predictor, you're okay, unless you want it to have a random slope. Then you do need to, because there's no way to unsmush the random slope without adding what is going to be a contextual level 2 random slope, which is a thing that is barely a thing. That's all I want to say about that. It's a mess to estimate, and you don't want to try. That'd be my recommendation. Now, what I was asking is, let's say that you keep your binary predictor. Do you have to use the cluster mean at level 2, or are there other choices that might work better?
Yeah.
Other choices
other
potentially.
choices,
Yeah, so several of you are working with schools and district data. My guess is that districts have the statistics for every school as to what the proportion of racial composition is, gender composition, free and reduced lunch, other sorts of poverty indicators. Like, they'll collect information about the entire school, and that is probably a better source of level 2 information than the mean of the people who happen to be in your study. So the mean of the people who happen to be in your study is better than nothing, but if you have better, more reliable and complete data from elsewhere, I would use that instead.
Oh, I see what you're trying to ask.
Yeah, I got there eventually.
You did.
Yeah,
That wasn't
it's
your best.
garbage in, garbage out. I'm trying. I did not ask the question very well. Yeah, not that your answers were garbage. I'm trying to make a bad joke.
It was garbage.
Yeah, it's on me though. It's my garbage. It's my problem. Badly worded questions. Okay, you had an actual question.
Yeah, so in that case, like for what I'm looking to do then, is it better then to take like demographic data like the hospital would have on like who visits and the makeup of that people compared to within my clinic specifically?
I think it depends on what type of inference you're trying to make. So in a school setting, like, the context of the school is not just the kids who happen to be in your sample, it's everybody. So using everybody's data, I think, better captures the context. In your case, the hospital is serving a whole bunch of people for a whole bunch of different reasons. And if you're interested in the climate and processes of your clinic and the people who work in your clinic, maybe longer term data as to what the clinic does might be more reliable than just like the snapshot that you have, but I don't know that the rest of the hospital is necessarily as relevant.
Okay.
It's kind of a judgment call. But the point of the story is, if you see level 1 predictors without anything related to it at level 2, that's most likely a problem. That's the end of the story on that. Okay, other thoughts or questions? All right, this next one, easier question. How do you know if a level 2 effect should be called between or contextual? First off, what's the difference?
Controlling or not controlling for level 1 variable?
Yep. Controlling versus not controlling for the level 1 value of the same variable. Which one controls?
Contextual.
It's contextual. And how do I know if I'm in that situation? Is it the level 2 variable that dictates it? No. It is not. That's what makes this so confusing. It's the level 1. So I end up with a contextual effect at level 2 if it's paired with what kind of level 1 predictor in terms of centering? Constant. The kind of level 1 predictor that still has its between cluster information in it, at level 2, the contextual effect is the extra effect that's not already implied by that level 1 predictor. So then between is what you get if you cluster mean center your level 1 predictor, meaning you have not controlled for its original value because all it has is relative within cluster information at that point. So between has to do all the work at level 2. Yes. Yep. And Lord help you if they don't use those exact words. Then you just have to sort of figure it out. Because you'll see things like, oh, the school slope. Which one is that? I don't know, but I mean, you can end up with very different things. So like if you have 2 negative slopes at between and within, and the between one is more negative, then the contextual effect, let me go the other way, less negative. Yeah, if the between one is less negative, then the contextual effect is positive. Am I doing that correctly? I need numbers in front of me. Math people, I can't do it in my head. Okay, so then you end up like, is does it go up or does it go down? It's like, well, one of them is negative and one of them is positive. You really have to know like what you're talking about then to make the right inference. So that's why it matters. These two things sound a lot alike, but they're not. They don't mean the same thing. All right. Other questions or comments on that? All right. Then changing gears completely. So we're sort of moving up, like, what is it? Not Maslow's hierarchy. What's the learning one?
Bloom's taxonomy.
Thank you. Yeah, I can see like a visual in my head and the labels aren't there. We're moving up Bloom's taxonomy with respect to this stuff. So we're sort of at the application extension phase. But with respect to logits and such, we're at the bottom still. We're at definition land. Because you got to know the definitions before you can apply the definitions to other things. So a link function then, for example, logits, probits, logs, and others, what is its purpose when used in generalized models? And it's the same purpose whether or not the model has random effects. What are they for?
Makes them work.
Makes them work, okay. I'll take that as a starting point. Do link functions transform the data? They do not. It's the model, more specifically.
The outcome values.
Yeah, not quite the outcomes. Not quite.
The means?
Yeah, the conditional mean. That's a weird thing to think about, but it's like y hat is the thing that it's being transformed. It's not y. And it doesn't matter what distribution you're saying y follows. Link functions are a logically separate thing. Now, there's certain combinations that go together, but they're separate. So comment from the Zoomers, link functions are for bounded predicted outcomes. That's the key idea here. Link functions are used to predict outcomes that have a boundary, one or more boundaries. So binary data, the classic example we're starting with, binary data means you're predicting a 0 or a 1. But what the model is trying to generate is the probability that any one case has a 1. That's the conditional mean to be predicted. Probability is bounded between 0 and 1. So probability has a whole bunch of possible values. Some would say infinite between 0 and 1, but you can't go past 0 and 1. So we need a prediction function that understands that. And logits and their cousin probit, which we'll talk about probably today, if not today then Thursday, logits then take that predicted probability and stretch it out to range from positive to negative infinity, or 0 corresponds to a probability of 50-50. So then we can use our regular linear model and not break it. We can predict a logit of 2, we can predict a logit of 200. But when we back translate that, what's the phrase for that? What does back translate from logit down into probability? Inverse link is what that's called. Unlogit it is what I would also say. When we back translate that, the predicted probabilities will stay within bounds.
So something, maybe it's just the words I'm struggling with, is like it's transforming the conditional thing into something unbounded,
Yes.
but yet logistic regression is in fact like binding it, like, so it can't go past 1 though.
Yes.
So I guess for me, like conceptually, it's like unbounded, but it actually is bound at 1.
It depends on the scale of the outcome that you're talking about. So let me get to one particular slide that I want, and then we'll actually, yeah. So here is a picture in which I have probability on the y-axis. This is a linear model predicting probability directly that doesn't work, goes out of bounds. What we need is something that understands that the slopes have to shut off as they approach either side of the boundary. And so this is accomplished by predicting logits directly. Here it is. Predicting logits, which is that thing, the log of the odds of the probability of a 1 directly. Logits go on forever and ever in either direction. But when you back translate logits into probabilities, like this mapping right here, for instance. Logits are on the bottom, probabilities are on the top. The probabilities do stay bounded.
Okay, yep.
So like a logit of like 10 versus a logit of 15 is the difference of like 0.99 versus 9999999.
Okay, yep, that's a good picture.
I like this picture. I stole it. It's actually from your textbook. So I like that one, and I like this one too. It's just a different way of looking at it the same way. So logits are link functions that are used to transform outcomes whose conditional mean is bounded on both sides into something that is unbounded, so that when you back translate it into probabilities, they stay where they're supposed to be. And logits are used for binary outcomes. They are also used for proportions. So if you want to predict like accuracy or something like that, then accuracy, the worst you can do is 0%, the best you can do is 100%. It's the same problem. But in that case, you are using a different conditional distribution than if it were binary. That's the other side of it. We even asked that question. So logits, probits, and there's a few others that I'll mention very briefly are for binary. Logs, for instance, are for outcomes that have a lower boundary but not an upper boundary. So counts is the classic example of when you'd use a log link. Also, things like response time, maybe, where you can't go negative in response time. Outcomes like money or minutes of vigorous activity per day, right? You can't have negative minutes no longer, like no matter how long you stay on that couch. It doesn't take away the minutes you already have. So link functions are for solving boundary problems. That's one piece of this puzzle. The other piece of it is the distribution, and that is designed to map onto the outcome that you actually have. Is it discrete or is it continuous? For instance, like a 0 or 1, that's discrete. Counts are also discrete, 0 times 1 times 2 times. Some things are truly continuous, and a probability distribution that's truly continuous is a better match. Like the normal distribution is continuous. But if we're trying to use it to describe an outcome that's not, then that's going to be wrong to some degree. And what goes along with normal is the idea of constant variance, which if you have bounded outcomes, doesn't happen. The variance has to shrink as you get closer to the boundary. So you need a model that understands that and predicts non-constant variance instead. And that's the world of generalized, is what link function do I need to address the boundaries? What distribution do I need to better match what the possible outcome values would be? And once I solve those problems, then we can use the same type of linear predictor, as it's called, linear model with fixed and random effects as usual. Hooray. And if you're like, what the hell is she talking about? I teach a whole class on this. About two-thirds of the class is families of generalized linear models, and the last third is an introduction to repeated measures in multivariate and path modeling. So if you're interested in taking the structural equation modeling class, I would highly recommend this one either before or concurrently, because I talk about logits in that class before we get to them in SEM. And I talk about path models in this class before we get to them in SEM. So they work together. Okay. Questions, thoughts?
Yes, I have one question. So, in this case, we will have a conditional distribution for our level 1 residuals.
Yeah, I don't think you can call it residuals. It's like the original outcome all put back together.
For
again.
the original outcome.
Yeah,
Okay.
it's conditional, meaning after fixed and random effects, but I don't think you can think about it as residuals.
Okay.
Like the math people be like, no, that's not right, even though like conceptually it sort of still is.
Yes, that's weird too.
It is weird.
We have a conditional distribution for something. Okay, so if we have binary variables, that can be, or that will be Bernoulli distribution.
Right.
Okay, but then we know that the variance of the conditional distribution will be fixed based on the link function we are using, right?
In some cases, yes.
Yeah, because if we use a logit, we know that the variance will be 3.29, or
Yep.
if we use probit, that will be 1.
Yeah,
How-
we haven't talked about that yet, though. So, no probits allowed just yet. But what you're talking about is this idea where if we assume that the underlying continuous variable that gave rise to our binary outcome has a logistic distribution, which is what we're saying when we use a logit link, the variance of the logistic distribution is pi squared over 3.
Exactly. To me, what is hard to digest or understand yet, it is that we know that if we use the Bernoulli distribution, so the variance is a function of the mean. However, when we use the logit link function, the variance will be fixed.
Yes.
So to me, it is hard to make that connected there. It varies, the variance so varies as a function of the mean, will be fixed. It is hard.
It's
to try
it's
to
two
put
different
those
things.
together.
Yeah, so in this literature, you start to see the phrase model scale versus data scale. Because in logits, the variance is a constant 3.29 and it can't ever be reduced. But in probabilities, you're right. On the data scale, the variance is non-constant.
Okay.
And it's two different things. And so
Yeah.
like in this equation here, I have an E. That's because this equation is predicting y star, which is the underlying continuous variable that gave rise to the actual binary one. Binary doesn't have an E, but y star does.
Well, that makes sense. That difference between the model scale and the data scale
Yes.
can fix to understand what I'm saying. Thank you.
Yeah, it's tricky,
Yes.
but that's what it is. Job security, yeah. Yeah, I don't feel very secure, to be honest, when I start to wander into conditional distributions and residuals and stuff. I feel like I'm handling it, I'm just sort of up here waving my hands. But this shit is hard. This is even harder. The generalized class is the hardest thing I do, I think, on me, at least.
More than longitudinal?
Oh, yeah. Yeah, longitudinal is a labor of love. Generalized is just hard. But, yeah.
In consolation, I thought answering the third question, I was like, all right, like I get this.
Big picture is what I want you to hang on to. That's what link functions are for. So there's a whole bunch of details that go under that, but just know that when you're predicting an outcome that has to shut off on one or both ends, that's when you're in the world of generalized. And if you ever see a binary outcome predicted with any kind of standard model that doesn't have a link, that's sus.
I said run.
Run, yeah. The best it can be is not that wrong. That's the best case situation.
So binary
Binary is an egregious example.
always need a link function.
Yes, you do. Okay. All right then. I think we're done with the quiz stuff. Any other thoughts or questions on that? No? All right, we were in here. I don't think we did this, did we? We did a little bit of this. We didn't do other link functions. I think that's where we can. Do I want to do that?
20 was the last slide.
Yeah, 20 was the last slide because I got to this and said no, I don't want to. But it's only 112, so I can't dodge that yet. I'm trying to think the order I want to do this. Let's go to some slides. Why not? What? I can go either way. I have a plan. I have 51 slides and a 19-page handout. I've got a plan. I just don't know how. I want to execute the plan. Hello, Nathan.
Hi.
Welcome to class.
I have a question about probits.
Well, you're in the right place, maybe.
So, will it necessarily lead to the same estimated outcomes if you use logits versus probits at the end of the day?
Yes.
Okay. And is one more friendly to work with than another for random effect models?
In the world of Bayes, yes.
Okay.
Probits are better, from what I understand.
Okay.
Probits are Gibbsable.
Oh, because there's a closed form?
Yeah, that. Yeah, welcome to hand-waving Bayesian estimation with Lisa. Probits are Gibbsable, which means you can use Gibbs sampling in which the same distribution for the prior is the same as the
Oh,
posterior. Conjugate
priors, yeah.
something? Yeah, see, I'm like just floating around in the handling waters here with my, I need like arm swimmies, to, keep me above water in Baseland. But yes, to answer your question, there is another game in town with respect to let's go, yeah, we'll go with this. So logistic regression has a cousin called probit regression. And probit is another link function for binary data. It does the exact same thing in that it takes the conditional mean and probability and puts it onto a continuous metric that ranges from negative to positive infinity. And also 0 is the middle point. But probit is on a different scale. So the way that I explain probit, because this wording is a little bit confusing, is to ask you to remember back to your very first stats class, like in undergrad or maybe even high school nowadays. They teach stats in high school. I wish they would have taught that. Like, that would have helped me a lot. Do you remember in your intro stat textbook where there were all these tables and there was like z's and p-values, and so like here's the z-score and you look up in the table what probability corresponds to the z-score?
Yep.
That's what probit is. Probit is the z-score that corresponds to that level of probability using a standard normal distribution. That's what probit means. So a z of 0 corresponds to a probability of 50-50 right in the middle of the distribution. And as you move to the right, the area under the curve goes past 50-50 and you go up. So it's the z-score that corresponds to the area under the curve to the left for that level of probability. That's what a probit is.
I was going to ask a question, and I read the slide and it said it right there.
Yeah. And so this nasty thing here means that to go back to probability, there's not an easy equation. Like in logits, if you want to go back to probability, it's e to the logit over 1 plus e to the logit. In probits, you have to do integration. So you can do that in Excel using the cumulative normal distribution function, or in software where those functions are built in. Otherwise, it's going to be some kind of approximation. The idea of probit corresponds to a different distribution for the pretend underlying continuous variable that we don't have access to. Instead of saying that it's logistic, you're saying that it's normal. So that means the E variance on Y star would be 1 rather than 3.29. So here's a picture that I like, and I could not find it again, but I'm pretty sure I stole it from Don Hedeker about 10 years ago. So this idea of a threshold, the point at which your response switches from 0 to 1 in the underlying metric. If you say that the underlying variable that you don't have access to is normally distributed, that corresponds to a probit. If you say no, it's logistically distributed, then it's a little flatter, and that corresponds to logit. But if you change one scale to the other via a constant of 1.7 and 0.701 in some textbooks to be more specific, the predicted probabilities that you get back are equal to the third decimal place. It really doesn't matter. They're both different ways of taking a bounded outcome, stretching the probability out to something that is unbounded to be predicted by a linear model, and then reining it back in to stay where it is. And I've actually seen simulation studies looking at, well, what if the distribution isn't right? Like, you don't know. Like, you only have the binary data. There is no way to answer that question about what pretend underlying distribution you have for the real continuous version, because you don't have it. So arguments about which it should be, it's like 6 of one, half a dozen of the other. Now, why do I mention this at all? Couple reasons. Number one, probit is known as ogive in the world of item response theory. Several of you are going to be taking that class in the spring, and when you talk about normal ogives, I want you to be like, oh, that's probit. I know what that is. Probit does not have odds ratios because it's not made from odds. So if you want to do effect sizes, you got to do something else in probit land, and I'm not even sure what that would be. And probit is what you are stuck with in certain estimation configurations. So for instance, if you want to do structural equation modeling and you want to have binary item responses or binary outcomes as part of that, one way to do that more efficiently is through what's known as limited information estimation, which is where you're working on a summary of the data instead of the original data, and if you do that, you're stuck in probits. You don't get logits. If you do Bayesian estimation in M+ in certain versions of models with categorical outcomes, you only get probits, you don't get logits. So there are situations in which you're stuck with probit whether you like it or not. It can be easier to work with in Bayes land because it's Gibbsable, and that's the end of what I know about that. But we're going to stay in logits for the purposes of this class, and your very last homework assignment is going to be a binary multi-level model. That's what it's going to be. It's not up yet. I got to make sure that I can get all the answers across all the programs to match, and that is a non-trivial exercise. So logit is what you'll see. Probit also shows up, but they do the same thing. They're just on different scales numerically. There are two others that I just want to wave my hands at briefly. If you have binary outcomes that are heavily skewed towards 1 or 0, then these alternative link functions can be more useful. There's something called log-log, which is designed for outcomes in which 1 is more frequent. It looks a lot like logit and probit up until you get to about 50-50, in which case it doesn't decay as sharply because there's not as many 0 cases by which to estimate that side of the line. Complementary log-log does the opposite. So it looks like logit and probit from 0 to 50, 0.5, and then it sort of peters out rather than going all the way up to 1. And so those link functions are down here. All right, yeah, okay. I am going to skip this for right now. We're not doing logits, we're not doing ordinal yet, not yet. Okay, there. I wanted to get to the hard part. So, big picture here. We're still doing multi-level models for the same reasons as before. We have dependency due to clustering. We have the potential for both within and between effects of any one predictor, but we may need to pick a different type of model if we have an outcome that's not actually continuous. So we have choices for distributions that would go with our outcomes, and we have choices for link functions that make sure that our predictions stay within bounds. So up to this point in the slides, I've only talked about single level models. Now we get to the complexity of what happens in the transition from single level to multi-level. So the big one is that when you add random effects to your model changes scale. The way that I've talked about the idea of once upon a time there was an E and then we split the E into 2 parts and then we split that and split that, that's not what happens in these models. We add variance to the model anytime that we allow random effects to exist. That's one thing. Anytime that we explain residual variance, the model changes scale as well, because the total variance has to change. Estimation is much harder, because the conditional distribution not being normal means that the standard multivariate normal likelihood function that's easy is not going to work. There's no such thing as REML under full information, so we'll end up with potential bias in our estimates or standard errors and such if we have small samples. And pseudo R-square is pretty much gone. You can use it for level 2 things, but not for level 1 things. It's gone.
So if we're in doubt, previously we could REML it out. So
You cannot.
What do we do now?
You are stuck with regular flavor maximum likelihood unless you go into the world of pseudo or quasi likelihood, which is not good, as you might imagine. If you call something quasi, right, that means not good as, like ish. So yeah, there's under regular, there is no full information, regular true maximum likelihood of the REML style for these models. It doesn't exist. Okay, so here's an empty model for a binary outcome. I'm abbreviating my logit is the log of the odds of the probability of a 1 like this. So the logit of the probability of a 1 still has my cluster-specific intercept, which we can define with a fixed intercept and a random intercept. Composite equation looks like this. But what's not in level 1? That's normally here in my empty model. I'm missing something blue. E, yeah, it's not here. It's not there, not because it's perfect, but because we don't estimate a separate level 1 residual variance. In the Bernoulli distribution, which is the distribution that we're using for the conditional binary outcomes after we control for fixed and random effects, that only has one parameter p, the mean. The variance is 1 minus p. So the variance changes as a function of what p is, and we don't need to estimate anything for it. If you're in logits, what you will often see people do is a logit model scale intraclass correlation can still be computed if you throw in pi squared over 3 where the residual variance went. And if you ask, I think Stata does this, I'm not 100 on that. R does this for sure. And M+ will do it too, I think. They'll compute the logit interclass correlation this way. But we can't talk about probabilities with any of these numbers, because in probability land, 3.29 is not accurate. The variance would be a function of the mean. Intraclass correlations for other generalized outcomes vary widely. So I just found a new article by the same people that were already on your reading list, and I posted it to ICON and I added it to your syllabus. It's an updated version that focuses on how to do ICCs for other kinds of link functions, like count data, for instance. Funny story about that. So I once spent my vacation. Yes, I was actually on vacation while Jonathan was teaching a workshop. I had taught mine the week before. So I was poolside at a resort with Walt Stroop's Generalized Multi-Level Modeling book, reading that, because, that's what we do. And I read as much as I could and tried to understand it. It's a very great book, but it's a very hard book. It's very dense. And he worked at the University of Nebraska at the time. So after I got back from vacation, I'm like, can I just talk to you for like an hour? Because I had all these questions, like when I was reading the book. And so I sat there and it was like quiz show. I just asked him question after question and he's answering them. And I get to this part, and in his book, he has a Poisson model, meaning that it's for count data in which the mean and the variance are one number. And he threw a 1 in where the residual variance went to get an ICC. I'm like, where'd the 1 come from? Like, it's not a probit link, it's a log, and the variance and the mean are tied together, so it's not constant, so like, where'd that come from? He said, well, I got it from this book. So I went to the library and I got that book, and they had a 1 in it with no explanation as to how it got there. So I emailed the author and I said, on page, 467, you did this, where'd the 1 come from? And he looked, and I got a response back from him, and he said, yeah, I don't know. I don't think that's right, though. And that was the end of the story. Like, well, shit. Like, I just went through every expert that I know, and no one can tell me where the 1 came from. And I've seen it on other people's stuff, too. Like they didn't make this up. So it's almost like one of those references that got miscited like a long time ago, and it's just been propagated. But it wasn't until I saw that article and the one that I posted from 2017 to actually try to explain how you would get an ICC for any other kind of outcome. And they have a very different formula for what it would look like in Poisson that's based on the mean, which makes a lot more sense. So, you can't just stick a 1 or a 3.29 in all the time. For other distributions like negative binomial, I honestly don't know. It might be in these articles and I missed it, but it's at some point this just breaks down. So it's easy for simple cases like binary, but not as easy necessarily for every extension. Let's see. So if I have a model that looks like this, for instance, I have my level 1 predictor that's been within cluster centered. Cluster mean is a main effect. Maybe a cluster mean is part of a cross-level interaction. I can have a random intercept variance. I can have a random slope variance. All of that would proceed as normal. You can do likelihood ratio tests to add random intercepts or random slopes and so forth. No matter what happens, though, the residual variance is going to stay 3.29. So that causes the model to change scale. Don't want to do that one yet. Okay. The way that I think about this, let me get to, this one. This is what I want to get to. Okay. First off, the way we talked about the fixed effects has to change. In the models we've talked about up to this point, the fixed effect, whenever it has a random effect around it, becomes the mean of that. So like in a random intercept model, we say the fixed intercept is the mean of the cluster means. If I add a random slope, the fixed slope for that predictor is the mean of the cluster slopes and so forth. That doesn't work anymore in generalized land. The interpretation for fixed effects changes to become something that is known as unit-specific or subject-specific, and it is also conditional on a random effect being 0. So the way that I would interpret this fixed intercept is this is the expected mean specifically for a cluster whose random intercept is 0. It is not the mean anymore, but for binary data, at least according to Walt Stroop's book, he says it's closer to a median. So in the example that I did for this 6A, I have links to that book as well as a different book that talks about this for more information. So at the beginning of your results section, you would just need to add a sentence or two saying this, that all the fixed effects that have random effects to go with them are unit specific. They're no longer straight averages, but they're still estimates of central tendency. So that's one additional piece that you have to be careful of. The big one, though, and the one that I think makes it difficult in practice to do sequences of models and draw conclusions, is that the model scale changes every time. If you add a level 1 predictor, it should explain residual variance at level 1, but we don't have that anymore. It's 3.29 no matter what. So what happens is the model total variance has to increase in order for there to still be 3.29 left over. I can give you a real-world example of this. Some of you may have heard this before. Kohl's department store, where I get almost all of Hugh's clothes and my clothes, let's be real. That department store, if you pay full price, you are doing it wrong. There's never a reason to pay full price at Kohl's. Everything is always on sale, or there's Kohl's Cash or discounts or everything else, right? So like in the store, I call the price check machines, I call those inverse link functions, because they take you from logits into actual money. Like money is like in data scale probability, and logits are just logits. So if I'm the manager of Kohl's, and I have, let's say, a pile of shirts where I have to take $25 for these shirts. These are the good ones, like really, really high-end Kohl's clothes. Okay, $25. I can't sell it for less than that. I put it on sale. I say, well, the shirt is marked $50. Now it's half off, so it's $25. If that doesn't work, I say, no. The regular price was $100, and now the shirt is 75% off. It's still $25 when I get to the cash register. That's how these models work. It's like when you add in a predictor, in order for it to still be 3.29 variance, it's like, what did the model original Y variance put all together again have to be? Marginally. And all the coefficients increase as you explain variance, because the overall scale of the model continues to grow. So what that means practically speaking is that if you enter level 2 effects that are designed to explain level 2 variance, then it works like it's supposed to, because those things get estimated and they get brought down. But anything that should explain level 1 residual variance is going to cause everything else to increase instead. So you can't compare coefficients directly across models. They're not on the same scale. And I'll show you how that works in the example that I have, but not yet. Actually, yeah, we can do a couple models on that. So here is a formula. Here is a reference for where that formula came from, and other folks have talked about it as well, in terms of how, if you wanted to, you could actually correct for differences in scale across models. I'm not going to bother to do that other than just to point out that it happens. Okay, how are we doing? Want to see it happen? Seeing is believing. Here's the example we looked at last week. This is the opposite of example 4, in that we are predicting binary free and reduced lunch from math scores, because that's the data that I had, so please forgive me. The new example that I have for count data is not this. It's a whole different one. There's a whole story to that too. So last time, we're using, to start with, the binary version of this variable. We'll do ordinal in the second half of the example, where we looked at a single level model without a random intercept and saw that the fixed intercept in logits corresponded directly to the probability in the data if I don't have a random intercept. I always do that first to make sure I know what's being predicted, whether it's predicting the 0 or the 1. Then we added a random intercept. We saw that we can still compute an interclass correlation if we throw 3.29 into the level 1 residual variance. And the predicted probability given by the fixed intercept no longer matches the data. It's a different number. So in an empty model where a random intercept is included, the way that I would interpret this fixed effect is specifically for a school whose random intercept is 0, unit specific. The difference is the probability of 0.236 versus what it was without the random intercept, 0.30. So it is a different number, it means something different. First thing I'm going to do is throw in school mean math as a level 2 predictor, which I centered and rescaled. So I subtracted 50 because that was near the mean of the variable, and then I decided to divide by 10 because the numbers were getting too small otherwise. Math in its original form ranged from 0 to 83. If I left it like that, I would be predicting the change in the logit for a 1-point increase in math score, and that's going to be a very tiny number. So to try and make the estimation go a little bit better, I divided it by 10. So then the coefficient is going to be per 10 points in math. Reference school having a score of 50. So here's my level 2 equation for that. ME logit for mixed effects logits and stata is what I'm using to do this. I throw in my fixed predictor just the same as usual. In R, I'm going to go ahead and call it Glimmer. I don't want to hear any arguments, it's Glimmer. And it looks the same as Elmer with the exception of these two pieces. You have to tell it what distribution and logit and what link function you want. And this is adaptive quadrature points, which we have not talked about yet. So here's my slope in logits. It's negative. We'll start there. What's a negative slope mean? Softballs, because it's 136. What's a negative slope mean?
Reductive.
As x goes up, y goes down?
Yeah.
Okay, that's still what it means. But what does y here? We're predicting whether or not a kid gets free or reduced lunch.
So the chances go down, or they're less likely?
They are less likely to get free lunch if their school has higher math. That is true. But in terms of scale, what does this number predict directly?
Logits.
Logits. That's what we're going with. So we're predicting the logit, which is the log of the odds of the probability of getting free or reduced lunch. So the logit probability goes down by 1.44 for every additional 10 points math your school has on average. The constant is my fixed intercept in logits. So that's the expected logit of the probability of getting free lunch for a school that has a random intercept of 0 and a school where the mean math is 50. So doubly conditional. I asked for some extra pieces of output here to clarify some stuff. So next piece I have here is odds ratios. These are your effect sizes. In Stata, you add them by putting 2 little letters at the end of your command here. OR stands for odds ratios. So the tie between these numbers then I have labeled out in the margins. This is e to the logit slope, exponentiated. It's an odds ratio effect size of 0.24. This one is e to the intercept, which is just an odds, not an odds ratio. So the label here is a little bit confusing. The constant is an odds of a 1. The slope for math is an odds ratio. Note that it did not do anything to the random intercept variance to transform it because it can't, it doesn't work. In R, same information in terms of the slope and intercept and logits. I did this to exponentiate the solution and get odds ratios, e to the internally stored results. And so those match what we have here. So for demonstration purposes, I asked for some predictions. Here's some words that describe what happened. I have margins instead of doing this, but I have it in R here. So I used a function called prediction, which is a package actually, that works like stata in that you can ask for predicted outcomes for a range of predictors. So I have -1 in math, 0 in math, and 1 in math in this case. So the difference between these predicted outcomes is exactly -1.44, because that's what a logit slope does. It's the change in the logits for a 1-unit change in the predictor. If I take these predicted logits, though, and I unlogit them, inverse link them back down to probability, the difference in these probabilities is not constant for a 1-unit change in the predictor. So that's why you can't take a slope and talk about it in terms of probability. It does not work. What you can do is take your slope and logits, use it to generate predicted outcomes, and then convert those predicted outcomes into predicted probabilities to talk about them. Order of operations. Cluster mean math is a level 2 predictor, right? What kind of variance should a main effect of a level 2 predictor account for?
Random?
Random intercept. And lo and behold, it did. So I have a random intercept variance from before. Here's what it is now after putting in cluster mean math, a reduction of about 61%. It just means that there's a whole lot of relationship between schools' average math scores and their proportion of children who get free lunch or reduced lunch. So this all works the same in terms of how we're used to. We estimate a random intercept. We see how much its variance was reduced by level 2 predictors. The fact that it's a generalized model does not affect that. What does affect it, though, is what happens at level 1. So I threw in cluster mean centered math as a level 1 predictor. And since we're running out of time here, here's the point that I wanted to make. And then we'll make it in more detail next time. Here's what the solution was before. Look at the effect of cluster mean math. It was -1.44. The effect of cluster mean math now is -1.52. It should not have changed, because cluster mean centering takes your level 1 and level 2 predictors and renders them orthogonal. So it should not have changed. The reason that it changed is because within cluster math explained some of the residual variance, but it can't go down. It's stuck at 3.29. So everything else had to grow to compensate. So we have more random intercept variance than we did before, and we have different answers for the fixed effects than we did before. The model is not on the same scale. Yeah. So there's no pseudo R-square that would make any sense for this. They're just not on the same scale. But you can do your odds ratios, in which case is what I did. Party out in the hallway. And for those of you that are like, my head hurts, will you stop talking? Yes, here's some words. There's lots of words to help. All right. Questions? Hit me.
I think, so the interclass correlation, I think I know why it's a 1 versus a 3 point whatever.
Yeah, what's your theory?
So I think that when they use 1, it's on a standardized scale, because if you rewrite it, it's a translated, I had to look at, I'm looking at this right now, sigmoid function. And so that top number, the 3.27 is on a logit scale, and I think the 1 is on a probit scale.
Yes, 1 is probits, 3.29
Okay,
is logits.
so then I
Yes.
think I know. I'll explain, I gotta think of how I'm gonna explain it, but I'm thinking in pictures, and I need to find the words for the pictures.
Okay. Okay. Well, the article that I posted does have what the ICC would be under various distributions, and they've like figured it out because math. So I'm satisfied with their answers, but I just thought it was funny that like all these experts are relying on each other for something that not one of them knew why it was the way it was. So I know I have wrong shit in my book, but I'm pretty sure that like I could explain why I thought it was right in the first place. And now I know that it's not. But that's a problem for another day. Other questions? No. All right, 1:44. How about we call it a Tuesday? How about that? All right. We'll play with more logits and probits and everything else next time. And let me know if you need help with your homework. Due next Monday. Bye for now. Thanks for being here.